Hi, this is Mr. Spohn here, and today we're going to look at solving the three gas law problems mathematically. Hopefully you have a good conceptual or qualitative understanding of the gas laws. Now we're going to solve some problems using Boyle's, Charles, and Gay-Lussac's law. So we have three formulas: P1V1 equals P2V2, V1 over T1 equals V2 over T2, and P1 over T1 equals P2 over T2. So we're going to use these three formulas. We have 5-word problems. We're going to see how to determine when to use what formula and what we have to do. So let's just go right through. We'll do some problems. Problem number 1. We have a gas occupying 500 milliliters. Milliliters is a measure of volume, liquid equivalent. When we use our graduated cylinders or beakers in lab, that's what we use. So a gas occupies 500 milliliters at 20 degrees Celsius and 742 torr. What will the volume of the gas be if the pressure is increased to 795 torr, but the temperature remains constant? The key to solving this problem is the temperature remains constant. If the temperature is constant, we have to use Boyle's law because this is the one where temperature is constant. And look at it. Both of these formulas have a temperature in them. If the temperature is constant, then that variable will not be in the formula. So when temperature is constant, you want to use the formula that doesn't have the T in it. So we're going to use P1V1 equals P2V2. Now you might be a little confused. What on earth is a torr? And that might be a new unit for pressure for you. But if you read the problem, what will the gas be if the pressure is increased to 795 torr? So torr must be a unit of pressure. We know that 20 degrees Celsius is temperature. And I'm hoping that you know that milliliters are a measure of volume. So we have our variables here. We're using P1V1 equals P2V2. Right? That's because temperature is constant. And now all you really got to do is plug in your numbers. What do we know? We know that P1, the initial pressure, is 742 torr. We know the initial volume is 500 milliliters. We know that we're increasing the pressure to 795. So what's going to happen to the volume? And that's all we have to solve for. We plug these three known values in up here, P2, V1, and P1, and you just solve for V2 algebraically. So when you plug in your values, you end up with this right here. And we simply have to solve for V2. You do that by dividing both sides by 795, bringing that over. When you rearrange and solve for V2, you end up with 466.7 milliliters. That's how we solve the first one. Read the problem, see what's constant, figure out what formulas to use, and just plug in your variables. There's only these are only 4 variable equations, not super difficult. Problem number 2. You have 2,785 liters of propane. Liters is a measure of volume. Think 2-liter bottle of soda. It's the amount of something. So you have propane, and that's called C3H8. It's at 833 millimeters of mercury. What is the volume of the propane at standard pressure? 760 millimeters of Hg. So you probably didn't know what a millimeter of Hg was. I mean, I can't blame you for that. But barometers and pressure used to be measured with mercury barometers. So these are a measure of pressure, and you can kind of infer that from the problem. At standard pressure, so this must be a unit of pressure. Again, temperature is remaining constant. If temperature is constant, we're using the formula without a T in it. Both of these have T's. We're using P1V1 equals P2V2. List what you know. We know that P1 is 830 millimeters of mercury. We know that V1 is 2785 liters. We know that pressure, standard pressure, is 760, so we are reducing the pressure. What happens to the volume? We're just solving for V2 again. You plug in your values, and again you rearrange and solve for V2. So P1V1 equals P2V2. You plug in these 3 variables, and you solve for this one like you would solve for an X in math class. And you get 3041.5 liters. So moving on to question number 3, and this is going to be a different formula this time. So you have 50 milliliters of nitrogen at 25 degrees Celsius and a pressure of 736 millimeters of mercury. What volume will you have if the temperature increases by 35 degrees Celsius, assuming the pressure does not change? Okay, so in this one, the pressure is not changing. The pressure is constant. If the pressure is constant, we use the formula without the P in it. Both of these have P, so we're going to use Charles's law. We're going to use V1 over T1 equals V2 over T2. And there is one other trick here. If the temperature increases by 35, so the temperature is at 25, if it's increasing by 35, the final temperature is going to be 60 degrees Celsius, not 35, because I'm saying the temperature increases by that much from its starting point. So we know that the initial volume is 50 milliliters. We have 50 milliliters of nitrogen. We have the initial temperature is 25. It increases by 35, so the final temperature is 60. And now really all you're going to do is plug these numbers in and solve. We know V1, we know T1, and we know T2. So you just got to solve for V2 like you would an X. There is one catch here though, one caveat. When you're doing gas law problems and you're using temperatures, they always have to be in Kelvin. So I actually did plug these in, but I converted both of these temperatures into Kelvin. You have to convert temperatures into Kelvin when you're doing gas law problems. There's no other way to do them. If you have a temperature using Boyle's law, we don't have a temperature, so we don't have to worry about it. But whenever you're using these two formulas, Charles or Gay-Lussac, you have to convert all temperatures into Kelvin. And Kelvin always equals Celsius plus 273.15. So it's not hard. You just take the Celsius temperature, add 273.15 to it. So that's what I did with 25. 25 plus 273.15, and 60 plus 273.15. And again, we just solve for V2. You just need to get rid of this because you want V2 all by itself. So you're going to essentially multiply this side by 333.15. If you multiply that side by that, 333.15, you have to multiply the other side by 333.15. And when you do that, you end up with 55.87 milliliters. So please remember, gas law problems, you have to convert into Kelvin. Cannot do them. If you're not converting to Kelvin, you get a different answer. The answer is incorrect. If you're taking a multiple choice with me, that incorrect answer will probably show up as one of the options. Yes, I know what I mean. So make sure you convert to Kelvin first. Always convert to Kelvin. And number 4 is a good example of why we do gas laws in Kelvin. Same thing. A sample of oxygen occupies a volume of 160 decameters at 91 degrees Celsius. What will the volume of the oxygen be when the temperature drops to 0 degrees Celsius if the pressure remains constant? And I'm kind of debating in my head whether it's deca or deci, I forget. But either way, I'm going to roll with, actually I think it's deci. I think deca is DA. So I think that's 160 decimeters, but I'm not 100% sure. What volume will the oxygen be when the temperature drops to 0 degrees? So let's what do we know? Pressure is remaining constant, so we are using Charles's law, and we're using this formula again. And what do we know? Well, we know T2 is 0. What happens if we put a 0 in here? We get a division by 0. And that doesn't work. Even if we arrange it and bring the 0 up, this means V2 is 0. So we have a gas in a container with 0 volume. You're telling me you have a bunch of gas that takes up 0 space. How is that even possible? If you have particles, they have to take up some space. So this is why the centigrade scale does not work. The gas laws are based on thermodynamics and the Kelvin temperature scale. So we have to use the Kelvin scale when we're doing gas laws. Because we get weird little things like division by 0, negative numbers on here. The Kelvin scale is based on absolute 0. 0 is the coldest possible temperature where molecular motion stops, and theoretically we can't actually get there. So if you would actually take these temperatures and convert them into Kelvin, the problem would be perfect. 91 plus 273.15, 0 plus 273.15, then you can solve. And we did this on the other slide. So we just converted these temperatures into Kelvin, and we solve for V2. You're rearranging, you're getting rid of this by bringing it up, and you end up with 120, I'm going to say decimeters. So that's how we solve those, and the last gas problem is, of course, going to be the one we didn't use yet. Calculate the final pressure inside a scuba tank after it cools from, that's 1,000 degrees Celsius, 1 times 10 to the third, 1,000 degrees Celsius, to 25 degrees Celsius. The initial pressure in the tank is 130 atmospheres. Since it's a tank, the volume's constant. So we have a scuba tank, and the tank's not really going to change its size very much, so we're going to assume the volume of the tank is constant. If the volume is constant, we have to use the formula that does not have a volume in it. We're using Gay-Lussac's law. P1 over T1 equals P2 over T2. So when solving these problems, just see what's constant to figure out what formula to use. And then from there, list what you know. And once you list what you know, remember to convert into Kelvin. So again, these temperatures right here, you got to add 273 to both of them to go from Celsius into Kelvin. And then you plug them in. And we know the initial pressure was 130 atmospheres. And the initial temperature was 1,000 Celsius or 1273.15 Kelvin. P2 we don't know, but we know that the temperature cools to 25 degrees Celsius, or that's 298.15 Kelvin. And again, you solve for P2 by multiplying this side by 298.15 and multiplying this side by 298.15, just like you would solve for an X in math class. And you end up with 30.44. So that's how we solve gas law problems. And occasionally you'll get problems where I'm mean, and you're not always going to solve for, say, P2 or V2. Sometimes I'm going to make you solve this for T2. And how do we do that? If I give you a gas law problem where you need to solve for T2, well, all you got to do is cross multiply, just like you would in math class. And you end up with P1 times T2, right there, equals T1 times P2, or P2 times T1. You're just cross multiplying. And now to solve for T2, this becomes really, really easy. All you got to do is get rid of the P1, right? By P1, divide this side by P1, divide this side by P1. These cancel. So T2 equals P2 times T1 over P1. And that's called isolating the variable. And that's what you end up with. So occasionally, gas law problems, you're going to have to solve for a value in the denominator, and you can do that by cross multiplying, either before the problem set up, before you plug the numbers in, or after. It doesn't matter. That's your choice. Hopefully this helps you with gas law calculations. This is Mr. Sapone.